Okay. So let's go through the example. So in this example, we'll be looking at sort of an extension of this sort of Slackbot problem, but looking at Rotten Tomato reviews. So I won't go through this intro stuff, and I won't go through this. We're all familiar with how to import pandas by now. But we're going to be dealing with, I guess, one new module in scikit-learn, and that is naive Bayes. So I'll give you guys just a couple of moments to open the notebook. Are there any questions? Can someone hit the lights in the back? Yeah, that's it. I mean, if you can read it, I guess. Okay.
Yeah, how did you make your iPod?
You can, as part of the IPython, if you scroll up to the top, you'll see that there's basically an inline HTML element, which is just linking to a CSS file that's defining the styles in the sheet. So it's just like a typical style sheet. So we talked about Bayes' law, but naive Bayes classifier, really the critical feature of naive Bayes, and the reason why it can scale is because you have the independence of, it assumes all inputs are independent, so we can apply simple, just applying a simple product between two terms. And sometimes it's okay, sometimes it's not. Most of the time, there's a relatively independent, words are somewhat independent of each other, but oftentimes they're not. For instance, here I said muffin and cupcake are relatively independent, but banana, muffin, or banana cupcake are not independent. Because the meaning of these words together is different than the meaning of the words when they're separate. It's a separate entity. It's like Chicago Bulls is different than Chicago and Bulls. So the phrase Chicago Bulls actually used to be in Google when you would put in certain phrases that were connected. Like if you put in Chicago Bulls on Google years ago, like when it was much younger, it would actually give you like Chicago and it would give you Bulls, but it wouldn't give you Chicago Bulls because it's typical to solve this problem. Because it was using sort of a naive Bayes, and Google's a little bit larger than it was back then. But we're trying to do the best we can with the information we're required. We're trying to make the least amount of assumptions. We're always trying to make the least amount of assumptions and trying to make the least amount of assumptions in building our model. One sort of the quintessential example use case for this, for naive Bayes, is spam classification. So given an email, if you have an email and you know nothing else about the email, if the email contains the string Nigeria, or if it contains prints, or if it contains both Nigeria and prints, there's a high risk it's spam. And there's certain keywords, and this is why sometimes when you get spam email, you'll sort of see it, they put like $signs for S's, and they put all sorts of gibberish to try to bypass those spam filters. So sort of always just a cat and mouse game between sort of these naive Bayes classifiers and email classifications. But really, the word Nigeria is just a feature in our data set. So if we have an email with a ton of words, each unique word is a feature. So there's actually, if we look at a text, there are a series of examples of text. Say we have basically look at a few independent words. Each one of these, by the way, would be an instance variable in our training set. And we see there's some words that are repeated here. There's some words that are relatively meaningless, right? Like is not. Sometimes we call these stop words. So is not a. It doesn't really tell us much about any document's going to have these frequent words like the, and, or. But we talked about one-hot encoding, and we talked about transforming a data set when we have categorical variables. When we have strings, we sort of need to take that a step further. We want to basically, we have basically 3 examples of text. And we need to, for each of these words, we need to, this is sort of like one-hot encoding, right? Where we want to map the entire instance space, basically each of these observations to counts for each of these words. And there's a particular tool we use that called Count Vectorizer. And let's just sort of work through it together. Very much like one-hot encoder. So we have Count Vectorizer. Just do a simple if we declare a vectorizer and we say fit transform on a text variable, I'm going to comment the rest of this stuff out. We'll get to it in a second. And we get something that looks kind of funny. And the reason why it looks funny is because you can imagine that when we have a massive space of words, when we have a massive data set, it's mostly going to be zeros. So for every word in our document set, we have math, we have is, signing, etc. And we're going to have tons of these. So we're going to have all the way down to like however many words we have. And most of these columns are basically going to be entirely zeros, except for wherever there's a 1. And these are all going to be zeros, for the most part. And there's a special term for this. This comes up often in mathematics. We have what we call sparse matrices. And we call this a sparse matrix. Sparse because our non-zero inputs are few and far between, assuming that we have any sort of data set of any reasonable size. And it's very inefficient to have these massive matrices in memory. So scikit-learn will sort of break it down and express it. It'll express it sort of as a coordinate system. We can get back the feature names. If we look at vectorizer, we can just look at the let's get feature names. And these are the entire features. So it's mapped our feature space. These are just the columns. So just like with one-hot encoding, we went from one column with many observations. We're doing the same thing here.
So after doing this count vectorizer, why didn't they ever take exciting like one whole string as a feature? Well,
It's a good question. What do you think?
I mean, trying to look at elements, right, of the string, as opposed to the string itself.
I mean, you can imagine, I mean, how many possible permutations of strings am I going to have? If I have a string that has multiple words, yeah, there's going to be a massive number.
If you have more than one count, is it just zeros and ones in sparse matrix, or could it be threes and twos and zeros?
It's a great question. Yeah, there can be twos. We'll see that in a bit. There's actually, so let's transform this. By the way, these some of these tools, some of the modules in scikit-learn have both a fit and a transform. This is the same thing as calling fit and then transform sequentially. It's just often that when you do sort of this chained execution, it will. It's just like basically 2 steps in one. I'm going to store this in a variable x. And we'll come back to this in a little bit. But we've transformed our data, and we noted that it was shown in this sort of sparse. Oops, that it was represented in the sparse format. So if we print x, we'll see this odd sparse format that x represents. So this sort of snippet of code here in your notebook sort of shows the comparison. NumPy and pandas all have these sort of built in. So X is the compressed sparse matrix that was output by default. It has a specific type, sparse matrix, which I believe is actually from SciPy or NumPy. And you can convert, if you call x.toArray, it'll just convert that back into, it'll sort of decompress that sparsified matrix. And we can just transform that back into a data frame. Again, this is stuff that's familiar. We've all done this, almost every lecture where we're transforming data sort of back and forth between matrices and data frames. So when we do that, this is the sparse matrix represented as a data frame. And this is obviously a very small matrix. But we do have one instance where there is 2, right? And I'll sort of go back here and I'll sort of paste in the text so you can sort of see what this matrix represents. I'm in the wrong. So we have 2 instances. We have, for each of these sentences, so we have 3 observations, right? These are my 3 sentences. This is sentence 1, this is sentence 2, sentence 3. So if we broke it down, math is great. And then here we have math is really great, which is just an addition of the really. And the last one we have exciting math. So you're seeing 2 here. So you can, it is actually sort of it's a count. It's sort of similar to a cross tabulation. And again, this x, this is really, we can treat this like, we can apply the same classification, the same training algorithms that we've applied so far. We can apply the same concepts to these values of x. It's the same, it's just a data frame, and it's interoperable with pandas, and we'll see that in a bit. You have, as of this weekend, a new CSV in your data folder. Go ahead and read that in. It'll take a few minutes. Take a breather. Decompress from all this probability nonsense. And this is real data. This is directly from Rotten Tomatoes. If you can't load it, or if you're having issues with the notebook, ping Deepti or Josh, and they'll help you sort it out. So we preview the data set as always, and clearly this is different than what we've seen so far. We have text columns, and we'll basically boil down this problem to a very simple objective. We want to predict. So by the way, for those of you who don't know, Rotten Tomatoes has this convention where they call, I guess, movies that are thumbs up is like fresh. So fresh is like thumbs up. I think thumbs down would be rotten. So we're only going to look at fresh and quote variables for now, and we're going to see if we can predict whether or not, given a quote, we can see if we want to see if we can classify whether it was a positive or negative review. And this data set comes from Kaggle. There's just sort of a note. So there's all sorts of, this was a pretty popular submission on Kaggle. So it was actually a slightly more complicated data set than we have here. It was slightly simplified for this example. But again, same conventions we've covered so far. X is an array. So we have the number of words, the number of unique words in our array is the number of columns, that is the number of features. And the number of reviews is the number of rows. Y is the same, Y is basically 1 is just whether or not it's fresh or rotten. And we loaded this into the critics data frame. So now, you can imagine that if quote itself is just a series, and let's use the count vectorizer again. I'm introducing a new named parameter here that's called stop words. We can specify certain words to omit from our data frame. So certain words that don't really tell us anything. They don't add information in the of and is. None of that is useful. So we'll cut that out. I'm just sort of like bringing it down to one line. And again, same process we did before. Fit transform, critics.quote. So we're storing it in a variable called x. And by the way, add your own comments. Just don't like stare at the computer screen. Add comments as I go along. Just sort of fill in your own understanding. That way it just sort of reinforces what I'm talking about and gives you a point of reference in the future for when we're going to have this data set's going to be on our, not the next homework, but the one after. So we're transforming the y into a type integer, just to keep it 0, 1, make it easier to process. And I want you guys to print out. So let's look at the shape of x before we do anything else. Name critics is not defined. So look at the shape of X. 14,072. So what are each of these? Which is which? How many features do I have?
21,700.
Yeah, I have a ton of features. So print out a data frame. Produce a data frame. This should be simple. With 20 features. And with the first, I'll say the first 20 features. And the first 10 observations. And you're going to have to use a technique I used in the previous cell. We're sort of decompressing the sparsified X vector. And it should only take, I think, maybe 1 or 2 lines of code. When I convert it to array, I get all zeros, which makes sense. Let's preserve the columns. So from our vectorizer, if we look at the vectorizer that we use to remap our features, has a bunch of methods on it. One of them I think is get features, get feature names. So the length of get feature names is basically, it's a list of all of my feature names. If I just look at if I subselect the first 20, so these are the first 20 features. Notice how they're alphabetized. So our first 20 features, and I'll say columns, first 20 features. And it's zeros, and that's sort of obvious why. because these are very rare words, but just gives you an idea. Let's look at the end, just for the heck of it. So again, what I've done here is I've just taken x. X is my sparse matrix, and I've indexed it for the first 10 rows, the first 20 columns. I can do the same thing by just reversing this. So let's look at the first 10 rows, the last 20 columns. Did I? Yeah. So I'll post this on Slack. I'll post this first bit on Slack. So suppose x is a NumPy array. Nice. Love it. Did you find that or did you create that? Did you? Nice. And so when we sample the last 20, we get just all the z's. Let's not do 20. Let's do like 5, a little better. Okay, so that's more or less how Count Vectorizer works. There's one more thing that I want to show you, and that is you can, like you said, Aaron, you can include more than one word or more than one combination of word. Sometimes you want to look at, say, pairs of words rather than just words individually. And there's a particular argument. There's one argument that we can pass to the vectorizer to enumerate those values. Where was I? To IPython can be a bit annoying at times. I mentioned stop words, but there's an additional option that allows us to sort of add pairs of words. Do this on the fit. I think it's n-gram range. So we call these n-grams. We call individual words, or we call sort of pairs of words n-grams. So if we have a word like banana muffin, this is called an n-gram. And we include n-grams because there's just some words there's some pairs of words that are sort of words in themselves. Like Chicago Bulls is an n-gram. And forget I need the comma. Yeah, it's n-gram range. And so if we call past 1, 2 to n-gram range, we're passing basically all the possible pairs. And so it quickly becomes, it very rapidly increases the size of our feature space. The benefit is that we get a larger, we basically get a larger feature space that includes possible interactions between terms. Let's look at how it looks on the count vectorizer. So if we print this out, if we just print out the feature names, now we have all the possible interactions. So just sort of clean this up. So again, we haven't done any fitting of our model yet. This is just pre-processing. I mean, the drawback of dealing with text data is that there's going to be a larger burden of pre-processing our data. Just cleaning it up. I mean, the data is inherently less structured. So now we've added every possible interaction term. So we get exciting math. What does this remind you of? What have we sort of seen something kind of sort of similar like this before? It's not what I have in mind, but maybe. It's kind of like polynomial features, isn't it? And polynomial features was basically finding all the interaction terms between my polynomial, right? So if I had two variables that were linear, like x and x1 and x2, polynomial features transformed it into x1 squared, x2 squared, x1 times x2. And this is sort of doing the same thing, right? I have an interaction between exciting, so sort of like x squared, exciting math, great, etc., etc. But it does respect order, right? So it's not going to do math exciting because it never sees math exciting. So it does respect the original order. It also lowercases them, so all my characters are in lowercase, just for comparison, so that any sort of string equality that I do is going to be in consistent casing. Okay, so I'm almost done with my pre-processing. I sort of want to hand over the reins to you guys on the next sort of cell here. We have a classifier, we have a function, I've created a function here that trains and scores basically a classifier. We pass in a classifier to a function, we pass in an x, we pass in a y, and we get back basically just prints out all the scores, all the metrics we've been talking about so far. It also times them, so it also computes sort of like a stopwatch where it takes the start time before it fits the data, and a stopwatch after it fits the data, and it does the same thing for scoring the data. So it times the fit and it times the score. So again, we're just going to test a few basic models. We have multinomial naive Bayes. There are two types of naive Bayes that scikit-learn adopts. There's the multinomial naive Bayes and there's a Bernoulli naive Bayes. We're not going to go into depth with the theory between the difference between the multinomial naive Bayes and the Bernoulli naive Bayes, but we'll talk about it a little bit in a second. But I want you guys to run this and let me know what you get for your timings and let me know what you get for your scores. By the way, note that in addition to naive Bayes, we're doing a logistic regression and a k-nearest neighbors. So this is what I mean, that our input data is in a compatible format with logistic regression and k-nearest neighbors and any of the other classifiers. We're going to sort of see some of the trade-offs between using naive Bayes versus logistic regression and KNN. Yep.
So it's to use logistic regression and KNN. It's words.
There's still a notion of distance. I'm not saying it's a good idea to use logistic regression. We're using it for the basis of comparison, but we are able to use it. It's not that bad.
But the distance, measure the distance up.
0 or 1. Or I mean not 0 or 1, but basically we have
Oh, it's a ball.
these.
Right, okay.
Yeah, we have a very large, we have our input space exists in, I think, 250,000 dimensions.
But as you noted,
So-
all these specification methods, they're not good at binary data. So it's not continuous.
Yeah, you're probably going to have some, there's going to be some, in fact, that's why logistic regression, likely the reason why logistic regression is performing better. Hopefully, is that what you're getting? The logistic regression has a better score than,
Well, it's close to multinomial.
yeah.
That's the-
So what's interesting about k-nearest neighbors? Look at the timings for k-nearest neighbors. Well, I guess, look at the timings for k-nearest neighbors between training and scoring and between all the others.
That's what you're saying. It doesn't really train.
Yeah, the training is basically, it's almost zero time for training, but the scoring is high. The reason why the scoring is as expensive as it is because it has to, every time, for every score, it has to look up all of those and all those features, compute the distance between a massive distance set. And this is why, this is just one of the drawbacks of KNN. So yeah, KNN didn't do too bad. It's interesting that KNN did as well as it did, but logistic regression also didn't do too bad. And we're using two different types of naive Bayes classifiers. One is called multinomial Bernoulli. I'll send out. I don't have the time to go into the depth of the theory between them, but basically, as you noted, when we're computing naive Bayes, basically what we ultimately get is we get something that sort of looks like this. We get an equation, basically boils down to something that looks like this. And the problem with this sort of format is that if one of these variables, if one of my features is 0, then basically my entire probability is 0. And so multinomial and Bernoulli naive Bayes basically sort of shift and they reformat this, they represent it in a different way so that you don't have a multiplication by 0 throwing off your entire probability. The difference between multinomial and Bernoulli naive Bayes is that most of the time, at least 90% of the time or more, you'll be using multinomial naive Bayes. Multinomial naive Bayes was designed for larger documents. Its score is almost always better. It's typically a little bit, I believe it's typically a little bit slower. Bernoulli is better for shorter documents. So for where we have shorter documents, less number of documents, and a small dictionary of words. So if you're dealing with, in the case of our Slackbot example, we would probably want to use a Bernoulli because there's a small vocabulary with a small number of data points. But for most intents and purposes, the interface is the same. In fact, we saw that here with Bernoulli, where the accuracy on our test data was lower, both training and on test with multinomial and between multinomial and Bernoulli. So I want you guys to try to improve. Let's try to improve this accuracy score. What can we do what are sort of our degrees of freedom for improving this accuracy score? How might we do this? What's interesting, the difference between, one of the great things about naive Bayes is that it's a very, very simple model. With logistic regression, we had all sorts of parameters, we had all sorts of knobs to tune and turn that affected the performance of our classifier. Naive Bayes has almost none. So that means that the performance of your model is largely going to be predicated by the format and the condition of your input data. So if you have input data like the number of features, all the stuff that how you format your data, how you remove features, how you add features, that's going to basically be that will be what determines the output of your Bayesian classifier. Let's actually talk about, before we go through that example, let's actually look at the example of using k-fold cross-validation. We went through this in a previous class, but basically we had one function called train test split, in which we could basically take a data frame, take some input vector, and specify a test size, and it would just do a very simple split. So if this were if this were my test example, I'd do like a split here and then say, that this is test and everything else is train. K-fold validation does the same thing, but it does it multiple times. It does multiple splits. And so let's say we have our input vector and we have n folds. It's the same, the arguments shuffle in random state, the same as they are in train test split. So when we do that, we're doing the same analysis that we did before. I'm just plotting different scores that I get. So get 0.675, and I'm just doing multinomial naive Bayes right now. So I'm just taking the best classifier from my previous cell, which is multinomial naive Bayes, both by performance and by score, and I get something that's sort of consistently between 0.76 and it peaks at 0.782. Let's see what this looks like. How do we know what the right value of k to use is? What do you think our result is going to look like as we change k? Right? Because I just sort of arbitrarily chose 5. It wasn't really a good reason I chose 5. But what if we just wrote a loop and we looped through all the possible values, or I guess k between 2 and 20. This will take a lot longer to run. And as we get to less, we sort of see a trend. So this blue line is my training error. My training error is basically 1. It's almost, I think it's like 99% accuracy. But as I increase the number of folds, I asymptotically reach some I sort of hit saturation on my classification score. Why do you think that is? Again, I should label the axes, but the axes here are number of splits.
You're just using the same data.
I'm not necessarily using the same data.
Similar data.
But even if I shuffle it, so let's say there's a variable, by the way, random state, and if I do random state plus I, it should, unfortunately you can't quite see it. If I do random state plus I, in other words, I'm going to generate I'm going to shuffle my data differently every time. So every time I'm doing this k-fold validation, I'm shuffling my data. And it looks similar. Not exactly the same. I mean, it's a little kink, but it looks similar. So basically, after a k of like 5, I'm not actually getting a performance increase. And there have been some examples in literature where it's rare that you see anyone split more than 10, although sometimes there's some data sets. But think about what's happening in terms of my, I guess, instance space. Like when I split into thinner examples. I mean, this distance, the difference between the blue line, if I took the blue line and I subtracted the green line, this distance is basically what I call my out-of-sample error. So this is my testing set, this is my training set, and the difference between them is pretty significant in this case, but this is what I call basically my generalization error. And so my generalization error, I make more and more splits with smaller and smaller input data, but because I'm averaging over a larger number of test samples, I'm actually converging to sort of like a true test error. And you can imagine, like I could sort of go to the extreme, right? I mean, if I went to say k equals n, in other words, if I split for every single one of my data points, and I averaged all of them, it's almost as if I'm sort of equalized my training error sort of evens out at what its true value is. Sorry, my testing error evens out at what its true value is. We talked about using sort of what we called n-grams to increase the number of features. And let's try doing that on this data set. We did it on the simple math is excellent whatever data set. Let me do it here. So in other words, here we're including any words, any pairs of words that are both 1 and 2. We'll increase it up to 3. We probably can't go any higher than 3. So in other words, we're including certain groups of words up to the maximum number of 3 words per n-gram. So like Aaron, like you asked, there are some cases where maybe we don't want a full sentence, but maybe we want groups of words that are related. Let's try it with a group of 3. Let's stop. So I've reshaped my data. And by the way, if I do x dot shape now, it's going to be some ridiculously large input vector. So I have 352,511 features. That is my input exists in 352,511 dimensions. It will take longer to run as a consequence of the fact that it's an absurdly large data set. And look at my training error. What's happening? Just sort of given this graph, and it's sort of difficult, I guess. There's actually, the blue line is up here. It's just sort of like overlapping with the axes. So our fit chart, this is called a fit chart. Similar but different. What happens when I increase the number of features? I increase the number of features.
Start over with it.
My out of sample error is higher than it was. And it's still pretty high. It's still overfitting. It was overfitting before, I guess I should say. And it's overfitting more now. Because I've increased the number of features, it has more leverage to overfit because it has more features with which to sort of, has more rope with which to hang itself. There's more features. So the training set, because it has tons of features, the training set, just like with linear regression and logistic regression, when we increased the number of features, we went from linear to quadratic to a higher order polynomial. It had all these features with which to fit the data. And it could sort of connect the dots. And it could build a model that very exactly fit the data points. But it was a little bit too good to be true because when we go to our test data set, basically everything sort of went to shit, and our error, our out of sample error, went up. So I want you guys to play with this. I want you guys to use. We learned a few new things with this, with the count vectorizer and naive Bayes. So you're all familiar with transforming the input data. It's way too large. So we went through a few methods. We went through improving the model, or methods / parameters which to play with. We have n-gram range. This is the number of words per, number of allowable words per feature. In this case, from 1 to 3. We have stop words. And that's the number of, I should say, words that are commonly used, sort of meaningless words. In the vernacular of decision trees, we would say that these are very low entropy words. They don't really tell us. We don't gain any information by including these words in our feature set. What else? What can we leverage from what we've learned so far? Maybe you can apply, this is sort of an open-ended objective. I want you guys to play around this, break stuff, explore, and find ways, see what improves your model, see what's a detriment to your model. But before we do that, I realize I forgot to go to break. So let's go to break and then come back at 9. And I'm going to post this updated. Data set on Slack as well.
Everything, I should just stop the kernel to clear out everything.
I would stop the IPython notebook because you can restart the kernel. Yeah,
Oh.
yeah, you
It
can
doesn't
restart the
seem-
kernel if you're.
It doesn't seem to clear out anything.
Do cell and do run all. And that will rerun each
Okay.
cell sequentially.
It's getting this for some reason.
Yep, that's when one of the cells calls the question mark after the. It's one of the first few cells. It calls it on count vectorizer, so that
So
pops
one of
up.
the things I keep seeming to get is I've got, when I'm pulling a text through, I seem to get all these numbers in with words, and I'm trying to figure out.
I
where
think that's just the
coming
way
from.
it sorts
Is that the
it.
data set? Is that just
Well, it may. I think the data set is. Do you have ngram of 2? Or you have
Yes.
ngram?
engram 2?
I think
Alright,
basically
sorry.
it's. I'm not 100% sure, but it might be sort of like if you have, say, A1 all the way through like to Z, it might be doing AZ, AB. You know what I mean? AC. It might be mapping this, or vice
Okay.
versa, like ZA.
But the numbers are just the order that they show?
Well, I mean, this is a real data set, so it's sort of like that means that someone within the review is putting like a 0, 0, 0. So it's just garbage in the data.
Okay. That's what I was wondering. So it's just like, I mean, it could be like
That means like
20,000 leads into the
there's-
sea or something like that, but I don't, I was just trying to figure
yeah,
out.
I mean, there's 48,000. There's 48,000 reviews, and so there's going to be some of them that just have maybe gibberish. I mean, it could be for all like.
Okay.
This-
If I chose like
whatever.
different 20 rows somewhere further down, I could potentially eliminate that garbage.
Yeah, you could. Yeah. Assuming it's garbage. I mean, there's also going to be like somewhere just like movie names that have weird titles or whatever,
Right.
or if they were, yeah.
You're not just leaving
Hey, Aaron, would you get the banana?
they had it earlier. Yeah.
You missed out.
What?
Said you missed out.
Yeah, there's that snacks code like right under it's always locked.
Yeah.
It should be full.
Yeah, I saw that. I mean, it's
Shows me this is your medium artist popularity. It's the age, so as you age, the artist is going to become less and less popular. Until they kind of like give like third. I say the same thing.
well, like, people go back. I think the larger it is, the more popular.
It's a medium artist popular, so central.
Medium artist popular.
Central. So yeah, central.
Right? So,
No, central. Zero.
Central media.
So it's like you're 550. You don't listen to any artist. What do you recommend? Anyway, it's cool. With that spot for you.
I really like the way that they did that graph.
Cool, right?
It's very cool.
Polar graph.
His name.
Yeah, it's like cool.
The guy from the New York Times is like,
Is it
he's like an E3 expert.
is it an upshot?
I don't know. I was just actually watching Anthony sent that, but I'm not sure. He's focusing sort of
Oh.
pay attention.
Yeah, I saw it. I didn't watch it.
You mentioned it.
That's good.
Who was the dude that you sent out that video?
This week? I don't know.
He's just a data scientist as well.
I just liked his lecture. It was a good lecture.
Yeah. It was 2 years ago though. So
Yeah.
it was,
Still relevant.
Bank of words a technical term, or is it just something?
It's a technical term.
Is it like meaning
It means it's basically the vocabulary. Well, that, yeah, so basically
ordered in a certain way or unordered?
typically unordered.
So it just doesn't matter how we order them there. Consider the same type of words as they are there.
It will, scikit-learn will, with the count vectorizer, will sort it just for indexing. So if it needs to do a lookup, like if you need to like look up a word, it makes it faster. But that's the only reason it's sorted. For the algorithm, as far as I know, does not use the sorting at all. What's the highest score? What's the highest classification score anyone's gotten so far? So one more thing I want to discuss is we talked about stop words. We had some words that are garbage. But what about the converse, where we have words that are important, or words that are more, clearly some words are going to be more meaningful than others. And so how do we quantify, how do we measure the, really I guess the strength of the word? In regression we apply different coefficients to certain variables to sort of recognize, to basically bias our model towards hopefully features that were more meaningful than others. There's a section in the notebook, how might we improve the model? And there's a notion of measuring how frequent words occur and how, I guess, noisy other words are. So just as we have noise with continuous variables, and just like we dealt with noise with KNN in all of our regressions, we deal with noise in classifying data because there's plenty of noise in text, particularly on the internet. And typically the procedure for doing this is known as TF IDF, which stands for term frequency inverse document frequency. Common here, because they're two separate concepts. And it's composed of two things. We have term frequency, and that is how frequently does a given word occur in a document. And by document, what's a document in the case of our reviews? It's what? Yeah, so a document in this case is we have a bunch of reviews. So we basically have a reviewer. We make some review. This one sucks or whatever. There might be certain words that are more interesting than others. But there may also be, not necessarily even stop words, but there could be some words that are occurring in multiple sentences. And they don't tell us much about the data, or really I guess they don't have much predictive value. And we can measure this by measuring the frequency that they occur across documents and between documents. And the term frequency, this is typically denoted as term frequency of a given term, is the number of times it appears in the document divided by the length of the document. So this is the normalization factor. This is the number of total words in the document. We call this the term frequency. And we have the sort of the opposite of that. And this calculates the frequency of a word. In other words, how often this occurs. Maybe it's a meaningful word, maybe it's not. Inverse document frequency, on the other hand, it's a measure of how important, basically it's a measure of importance. IDF is a function, by the way, so IDF. Sorry. It's the measure of importance of a term, and it's expressed as the log, it's basically a log ratio. It is the log of the number of documents. By the way, this is a natural log. Just make it more explicit. It's a natural log. Number of documents containing T. So the total number of documents. The total number of documents. The documents total. Divided by the number of documents containing T. And the term frequency, IDF frequency, is the product of the two. So you take these two, you multiply them. So it's called TF IDF, where we're multiplying the term frequency times the inverse document frequency. We call this TF IDF. And this is a transform. This is a transform just like Count Vectorizer was a transform. It's taking our data, our input data, and it's transforming it into something else.
Let's say, like, just a thought, say you have like 2 or 3 reviews that say like those critics went on a rant and just said like, "Oh shit," 30 times in the review, and are an outsized contributor to the feature shit.
That's the normalization factor, right? That's the total number of words in doc. That's why this division factor exists, because otherwise, if this normalization factor weren't there, then yeah, it would bias towards long documents.
So the doc being like just the quote.
The doc in this case, in our previous example, the document would be the text within that observation. So the review itself.
Is there more formal definitions of the word document in the sense that it's easy to define it from the standpoint of this example? It's a little more complicated when you get into it.
It's, well, sort of like the equivalent of an observation, right? I mean, it's an observation of a given text. I guess.
What if you were reviewing scientific literature and you have all these publications, you're doing a review of a certain science, you're doing a review of scientific literature, you have all these reviews published. The document would be the actual, each individual publication.
So you would be, I mean, typically, we call, the terminology is we call a collection of documents a corpus. So let's say we have, this is the corpus, that is, I don't know, publications by nature. Publications in Nature Nanotechnology. In 2008. And within that, you have DNA classification. Whatever, using Bayes. And you have, I don't know, MEMS. Each one of these, this is the document. This is a doc. This is a doc. And you could break it down further. But typically, there's a collection of documents, and the collection of documents is known as a corpus. So in our case, the corpus is, we have a corpus of reviews. Each review itself is a document. Does that answer your question?
Yeah, I mean, the question's probably more theoretical
I mean, you're right. With text, you can sort of like split it. You can get like thinner and thinner. It's sort of like abstracting in terms of text because we're dealing with like numerical attributes. Like a numerical attribute was sort of atomic, but text is inherently, I guess, a little more weird to deal with.
You can make the for the number of appearances within a document, I guess, define document. We could probably comprise the examples or define document a little differently. It might appear more common. I mean, these are
Well, that's why.
one case, right?
But that's also why these normalization factors exist, right? Like the number of documents and the number of words in a document. So if a document is longer, it's not going to, hopefully, because you're dividing by the number of words, it's basically a ratio. The ratio of appearances of a word in a document divided by the total number of words in that document. So if you had, War and Peace, and you were doing text classification on War and Peace, then, a term, it would basically be normalized by the length of the
Okay,
document.
here's
So
a quick example. Right? So say within the corpus, you had different publications, and each publication had articles on specific genuses. So the DNA classification of cats using naive Bayes, and there were 10 articles within that particular publication, and the next one was DNA classification of squid using naive Bayes.
well, then that would be up to you. I mean, how you define your splits is gonna. I mean, yeah, you're going to have to be sort of. You should. Well, it depends on what you call a unit, right? Like what you call a document, right? And that's sort of circumstantial based on what the data you're collecting is. I mean, if you're looking at, maybe just looking at conclusions of articles. So I guess like there could be cases where, there are more complex methods if you really wanted to, if you had multiple splits in your data, there's more complex methods in naive Bayes for those types of applications, which we'll get into to some degree in this class. But you're right. If you have this complex taxonomy of documents, if your taxonomy of documents is more complicated than a corpus, document.
Maybe generally, like the Aaron's example, if you had specific 4 different comments and said, oh shit. That would count as
In nature,
four.
that'd be unlikely, but maybe.
Right, but I mean, to our specific, Fruiter example, I mean, if we had 4 separate comments, each of which is considered to be a document, right? Although that might have been the same person entering those comments at 4 different times. And I
But
guess
I think that's also signal. That's not necessarily noise. If it's the same person, there might be certain trends or certain biases or certain, I guess it's like you don't necessarily always have perfect information, but if you have, I mean, this is sort of like it's almost it becomes a very sort of abstract question, an abstract domain, but they do this on things like classifying, like looking at authorship, like historical documents, like looking at how many principal authors there were, in a particular book in the Gospels or whatever, and they can look at vocabulary usage and they can look at terminology usage, and it sort of becomes like an unsupervised learning problem at that point. But yeah, you can sort of see clusters of related information. Anyhow, I just want to finish on this example before we head out. Just like a very, very basic example, but just sort of like to illustrate TF-ID. It's a very basic calculation. So example is, we have a document that has 100 words, And within those 100 words, there's 3 utterances. We call these, sometimes in natural language processing, they call it occurrence or string of words, an utterance. And I guess it sort of goes back to your question, some of the sort of a recurring theme in this lecture that sometimes it's not necessarily clear how far we split our input words. So we have an utterance. We have 3 utterances of cat. And we have our number of documents. So n is 10 million. And word cat. So of those 10 million documents, there's 10,000 of them. 1,000 contain the word cat. So in other words, this is what we use to calculate inverse document frequency. This is what we use to calculate term frequency. So inverse document frequency is a measure of rarity of terms. This is how rarity of a term across multiple documents. And the term frequency is just the ratio of the number of appearances of cat in the given document, which is just 3 over 100. So this is the frequency of the word within the document. So just looking at our term frequency, the term frequency of cat in this example is just 3 over 100. And the inverse document frequency of cat is log, or natural log, of 10 to the 7 over 10 to the 3, which is ln of 10 to the 4, which I think comes out to be about 13 or so. So the product of the two are TF-IDF. Our TF-IDF is 13 times 3 over 100. And again, the product here, the significant reason why we're taking a product is that as one increases, you can it's sort of like F1 score. We need to have both rarity and frequency. So as rarity increases, if we held term frequency constant and we increased rarity, that the score of TF-IDF would increase. Conversely, if term frequency went up and we hold inverse document frequency the same, then IDF would go up. But basically it means larger is more significant. It means it's a more significant term. It's going to influence the prediction of our class more strongly. And so we did this in this case for one word, but we do this for each of the words in our data set. So we have some input feature x, and it goes through this transformation, which is TF-IDF, and out comes some transformed version of x, where basically it's sort of like feature scaling. So x here was maybe a sparse matrix where we had mostly zeros, a 0, 0, and then maybe a 1, or maybe a 2 every once in a while on rare occasions. And we convert it to basically the TF-IDF x, and this now has these non-zero values of our independent variable in our data frame, or in our input feature, are going to be mapped to some value, either increased or decreased. Maybe this one goes to 3, 0, 0, etc. And it gets applied differently based on the term, right? So it's not, this term here might increase, but this term here might decrease. So it's a transformation, a nonlinear transformation to our input data set. Before I go, I want to, again, just sort of emphasize the additional materials. There's a ton of stuff on this stuff, and it's just sort of the way it is. We don't have, I guess, the time or the flexibility to cover the details and all the vagaries of probability and Bayes' theorem. I strongly, highly recommend that you go through this additional exercise. It's using the weather data. It will give you a different perspective on classification. So when we're classifying with Bayes' theorem, we're sort of classifying in reverse. We're assuming that we have this input. We see some input data. We see some combination of sunny, hot, high, windy, etc. And assuming that we got that input data, or assuming that play were no, what's the likelihood that we would have seen that data? Or vice versa, if play were true, what's the likelihood we would have seen that data? And so I guess it just sort of solidifies what basically step by step, what each of the calculations are for the prior probability, the posterior probability of each of those events. So yeah, it'll give you more of a theoretical understanding of what naive Bayes is really doing. Because naive Bayes is abstract, and a lot of people apply it without really knowing, really fully understanding how it works or what it does, and why it's special and why it does what it does. Beyond that, there's all sorts of interesting additional resources. Some of them are more technical than others. The Stanford article on naive Bayes is fantastic. It's a lot more in depth. The visualizing Bayes theorem is more introductory, so start there and sort of drill down from there. Any final questions? No? Damn it. I have a question for you guys. Where the hell is this happy hour? Does anyone know where Foo's Juice? I don't know. I don't even know how to pronounce it. Barangio.
It's across the street.
All right. Well, I'm pumped. I hope to see you all there. Because I know this was a long lecture. What'd you say?
Oh, the exit tickets.
Oh yeah, preferably after drinking. Yeah. Drink first, then do exit tickets, especially after this lecture. Tell you what, we'll drink and then we'll come back and cover naive Bayes again, and then go back and drink. Okay. Yep. Finish your exit tickets, and I don't know. I guess we'll make it over there. So hope to see you there.